Look up at the night sky, and it feels timeless. The stars seem permanent, fixed points of light that have always been there. But that calm is an illusion. Stars are born, they grow, they change, and they die. And right now, deep inside cold clouds of gas and dust, new stars are forming, quietly, invisibly, and on timescales far longer than a human life. For centuries, astronomers understood how stars die far better than how they are born. Supernovae announce themselves with explosions brighter than entire galaxies. But star birth is subtle. It happens behind thick curtains of dust, hidden from visible light. To understand it, astronomers need patience, precision instruments, and a willingness to stare into the coldest, darkest regions of space. This is where a project with an oddly comforting name comes in: caffeine, short for core and filament formation/evolution in natal environments. Despite sounding like something that fuels late-night work sessions, caffeine may help answer one of the most fundamental questions in astrophysics. What controls how many stars are born? Stars begin their lives inside stellar nurseries, vast molecular clouds made mostly of hydrogen, with traces of helium and heavier elements. These clouds are enormous, often spanning hundreds of light years, yet incredibly cold, with temperatures just a few degrees above absolute zero. At these temperatures, atoms move sluggishly, allowing gravity to slowly take control. But not all clouds form stars efficiently. Some clouds collapse into rich clusters filled with thousands of newborn stars. Others barely produce a handful. For decades, astronomers suspected that the answer was simple: more material equals more stars. Pack more gas into a cloud, and gravity should do the rest. But the universe rarely follows simple rules. The Caffeine Survey, led by astronomers at the European Southern Observatory, is designed to test this assumption directly. Its focus is not just on star-forming clouds as a whole, but on their internal structure, especially filaments and dense cores. Filaments are long, thread-like structures of gas and dust that snake through molecular clouds. Thanks to missions like Herschel, astronomers now know that filaments are everywhere in star-forming regions. They are not random. They act like cosmic highways, channeling material into dense, knots called prestellar cores. These cores are the true cradles of stars. If a core becomes dense and massive enough, gravity overwhelms all opposing forces. The core collapses, heats up, and eventually ignites nuclear fusion. A star is born. But here's the puzzle. Not every filament produces the same number of cores, and not every core produces a star. Something more than just mass is at work. To investigate this mystery, caffeine targets regions like GL 316, a stellar nursery located within our Milky Way. What makes GL 316 special is its balance. It contains large amounts of cold gas, but it isn't yet overwhelmed by massive stars whose radiation could disrupt the process. Using the Artemis camera on the Atacama Pathfinder Experiment, APEX, telescope in Chile, astronomers observed GL 316 at sub-millimeter wavelengths. This kind of light is invisible to our eyes but perfect for detecting cold dust, the raw material of stars. The result is striking. In caffeine images, filaments glow in shades of blue, tracing dense, icy structures weaving through the cloud. Behind them lies a crowded starfield, observed by the VISTA telescope, showing the older stars of the Milky Way shining through gaps in the dust. This layered view reveals something critical. Star formation does not happen randomly throughout the cloud. It is tightly connected to the filament's geometry, density, and evolution. One of the biggest surprises in recent years is how fragile star formation appears to be. Gravity is powerful, but it is not alone. Gas pressure, magnetic fields, turbulence, and radiation all push back. Magnetic fields, in particular, act like invisible scaffolding. They can guide gas along filaments, slow collapse, or even prevent cores from forming at all. Turbulence, chaotic motions driven by supernovae, galactic rotation, and stellar winds, can either compress gas into dense pockets or tear structures apart before stars have time to form. Caffeine is designed to disentangle these effects by comparing many regions with different conditions. Some clouds are calm and magnetically ordered. Others are chaotic and turbulent. Some are rich in gas but poor in stars. Others convert material into stars with surprising efficiency. By studying these differences, astronomers hope to identify the rules of star formation, not just in our galaxy, but everywhere. Why does this matter? Because stars are the engines of cosmic evolution. They forge heavy elements, shape galaxies, and create the conditions for planets, and eventually life. The number of stars a cloud produces influences how galaxies grow over billions of years. If star formation were perfectly efficient, galaxies would burn through their gas quickly and fade. If it were too inefficient, galaxies would remain dark and lifeless. The universe we see today exists in a delicate balance between these extremes. Understanding that balance begins in places like GL 316. Another key insight from caffeine is that time matters. Star formation is not instantaneous. Filaments evolve. Cores grow or disperse. Some regions are caught in early stages, where material is gathering but stars haven't ignited yet. Others are more mature, already glowing with newborn suns. By assembling a statistical sample of regions at different stages, caffeine acts like a time machine, allowing astronomers to reconstruct how clouds transform over millions of years. This approach also helps explain why star formation appears inefficient on large scales. While galaxies may contain vast reservoirs of gas, only a small fraction is in the right place, at the right density, under the right conditions, at any given time. There's another layer to this story: feedback. Once stars form, they begin to reshape their environment. Even relatively small stars emit winds and radiation that can erode nearby filaments. Massive stars are far more dramatic, blasting their surroundings with ultraviolet light and shockwaves. This feedback can shut down star formation locally, but it can also trigger it elsewhere by compressing nearby gas. Caffeine observations allow astronomers to see where feedback is destructive, where it is constructive, and how it changes over time. The result is a picture of star formation not as a simple collapse, but as a self-regulating ecosystem. And then there's the human element. Projects like caffeine represent decades of technological progress. Instruments like Artemis must operate at extreme altitudes, under freezing conditions, detecting faint signals from dust colder than liquid nitrogen. The data must be carefully calibrated, combined across wavelengths, and interpreted using sophisticated simulations. Every image is the result of countless hours of observation, analysis, and collaboration across continents. All of this effort serves a deceptively simple goal: to understand how something as ordinary as a star comes into existence. When you see the caffeine image, blue filaments drifting across a sea of stars, it's tempting to focus on the beauty alone. But what you're really looking at is potential. Every bright knot could become a sun. Every filament is a story halfway written. Some of those future stars may host planets. Some of those planets may orbit in the right conditions for chemistry to grow complex. And somewhere down the line, a civilization might look back at the sky and wonder where it all began. In a cold cloud, in a filament, in a place like GL 316. Caffeine won't answer every question. Star formation is too complex for a single survey to solve. But it is a crucial step toward turning mystery into understanding. Because stars don't just light up the universe. They explain it.